Okay. It's me again. I'll talk a bit about this whole energy model idea that is quite essential to this whole energy aware scheduling work. So in this talk, I'll try to go through what this energy model is, how it's supposed to be used, and based on that, it hopefully makes more sense how to actually come up with the numbers, the tables you need to provide for all this code that we're building to work. So why is it that we actually need this energy model in the kernel? So as we already discussed a bit, the Linux kernel in its current state is mostly unaware of all P and C states. Well, each of the frameworks that deals with P and C states, they know about the states, but the scheduler doesn't, and no other part of the kernel does. So there is a general lack of communication and knowledge across the kernel. We have bits of information here and there, but there is no single place to go to, or there's no easy way to see all this information, and we actually need to coordinate all of it to actually make sensible decisions. So the plan is to change that. We need to coordinate things, and the plan is to coordinate it in the scheduler, such that the scheduler will have influence on frequency scaling, it will know about frequency scaling, and the same goes for idle states. And another motivation for actually having a model describing how the particular platform works in terms of power and performance trade-off is that the tricks you can do to try to save power or energy on your platform depends very much on the hardware. If you have multiple clusters, then it probably makes sense to try to consolidate tasks on a single cluster so you can leave the other one completely powered down as much as you can, as much as possible. But depending on how expensive it is to run at very high P states, this packing only makes sense to a certain extent. At one point, it might be more expensive to run on a single cluster at a very high P state than actually spreading across two. And the only way we can sort of do the right decision all the time is to have the information about how expensive is it to run at each P state and what is the cost of waking up another cluster. So if we have all this information in the kernel, we should be able to make the right decisions. And the model will provide this. As an extra bonus, if we have this table of information about all T and P states, we can use it in some of our tooling as well, such as idle stat. If we have traces saying when we were in which states, we can basically sum up everything, multiply it by some energy or power factor, and end up with an energy score. But that's not something I'm going to talk more about in this presentation. So, a model always has some limitations. It's never going to be accurate. We're not trying to do better than our hardware engineers and come up with a glorious single model that can just predict everything to a very high precision. What we're after is a simple model that can just help us make the right decisions. I mean, if we can get something which is right more than half the time, then we're doing good. We should remember that if this model is to be used in the scheduler, and that is the plan, it needs to be really simple because we're going to use it in critical paths of the kernel, so we can't have something which takes ages to compute. It needs to be as simple as possible. And the other thing is, and we have heard this argument a number of times, is that energy and power for an SoC is not just about the CPUs, but it's difficult enough getting it right for the CPU, so that's where we're going to start. The kernel doesn't really have good infrastructure for getting knowledge about power consumption in various peripherals and things like that. So for now, the focus is to get it right for CPUs. And by the way, if you have any questions or comments, please stop me. So, before we start describing the model itself, let me just describe how we view the system. We need a simple view, otherwise we can't come up with a simple model. So, things we need to know about for energy awareness is what are the power domains and what are the clock domains of the system. So on this simple figure, I imagine a 4 CPU dual cluster SoC. So we have CPU 0 and CPU 1 in one cluster, and CPU 2 and 3 in a different cluster. In the cluster, you have some shared hardware resources that can be your level 2 cache, other interconnect things that are shared between the CPUs, and you have the CPU cores themselves. So this is somewhat inspired on what by what we have on TC2. So the dotted blue line sort of indicate the power domains. So for each core, we can power gate each CPU, and we can also power gate the entire cluster, which will take down the shared hardware. And we can do that for both clusters individually. But for clock gating, we can only clock, well, the clock domain is cluster. So if you change the clock for a CPU 0 or 1, so will the other frequency change. So this is a very, very simple view of power management of the system, but I think it's probably good enough for what we want to do. So the thing we actually want to model is, or we can sort of put energy consumption of the system into sort of 3 phases. We have some energy we burn while the CPU is doing something, running a workload, it's busy, and we consume some energy while the CPU is idle if it's got nothing to do. And then there is these transition phases where you transition from a P state to a C state or back again. For the period where we are busy, that is the light blue on the slide, we can sort of figure out the energy if we know the power consumption at the particular P state and multiply by the time we spend in that P state. And similarly for the idle time, which is the green bit, if we know the power burned while we are in a particular idle state and we know for how long we're there, we can figure out what's the energy burned during the idle time. So the last bit is the transition phases. And it's not free entering and exiting idle states. So we need to take into account the energy burned while doing this transition. And because this transition time is more or less the same, well, that's my assumption, we can represent the transition energy as just a number. We can basically measure how much power do we burn by going in and out of a specific idle state. So we can sort of add up the total energy consumption by looking at the busy time, the idle time, and the number of transitions between P and C states. So that's the basic idea. So all this information about how much power we burn when we are busy and idle and transitions between states, we need to represent that in some way in the scheduler. The scheduler currently has what's called scat domain hierarchy. I've tried to illustrate it here, very simplified, but it's basically just a hierarchy of groups of CPUs. So at the lowest level, you have a group consisting just of one CPU. And then at the next level, you can have a bigger group that will encapsulate more CPUs. So it sort of represents the system topology. So for our 2+2 system from before, we would have a group for each of the CPUs, and we would have a parent group which would cover all the CPUs in a cluster. And we can use this hierarchy to attach some of all this power information. So the idea is that for the per CPU groups, the lowest ones, we would attach information which is associated with just the particular CPU. So there we would put information about per CPU idle states, whereas if we have cluster level idle states, we would associate them with the cluster group. And the same goes with P states. If you have per CPU frequency scaling, you would put your P states into the table for the group just for the CPU. But if you have per cluster P states, then you would put your P state information into the cluster group. So the information we need for the model is that for P states, we need to know the compute capacity at each P state. The reason why I put compute capacity and not frequency is that for big little we have this microarchitectural difference thing. So to abstract that out so the scheduler doesn't have to worry about frequencies, we can just put a number in there representing the compute capacity where we already factored in the microarchitectural difference. And for each P state, we do also need to know what is the basic power, basically what is the energy per second we burn if the CPU is running at this particular P state. And one thing worth noting is that for scheduling decisions, we don't actually need to know the true power consumption. You don't need to put a specific number of milliwatts or whatever in there. You can actually normalize all your numbers. As long as your normalization is consistent, you can put BOGO watts or whatever. You don't need to put your exact measurement in there. It just needs to be normalized. That's fine, because we just need to know whether a decision makes things better or worse. We don't really care about the unit. For C states, we need to know the power consumption.
That's a question.
Sorry.
Why 1,024? Is it not normalized 1,024? Any particular reason except it's a convenient power of 2 or something? Or
the reason is that when we do some of the multiplications we do in the scheduler code, to avoid overflow, it's nice to have the compute capacity as a fairly small number, because when we multiply by sums of loads and things, we might overflow 32-bit numbers.
So it's just a convenient number?
Yes, it is. Yes, that's the only reason, really. And a lot of other default numbers in the scheduler are
because everything else then scales with that.
Yeah.
Like saying the scheduler actually ends up using this in many default cases. It's an easy mathematical number.
No.
Quick shift and operate.
Yeah. So no, it's not a requirement for the model as in itself. It's just a convenient scale.
That you could have maybe used 4096.
Yeah.
Okay.
So yeah, that is the only reason. For the C states, it's slightly different. We still need the power number, but we don't really do anything while we're idle. So we just need to know how much energy do we consume in a specific idle state. But for the idle states, we also record the energy of doing a full transition from a P state into idle and back out. Now, the transitions always come in pairs. You can't really go into a C state twice without going out. So I think it makes sense to just record like a full circle, like going from a P state into the C state and back out again, and just record the total energy of doing that. As I said before, it's worth noting, or it's really important, that the numbers provided in the tables that we put into this hierarchy, the power numbers we put into the table associated with just the CPU group, it needs to only have the power consumption of that CPU. If there is cluster level power consumption, it should be accounted for in a table associated with the cluster itself. So the rule here is that whatever data you put into the green bit associated with the group should be the contribution by that group alone. So, for example, in TC2, if you have CPUs in WFI, then each CPU will leak a certain amount of power while in WFI, but at the same time the cluster might be up. So the power associated with what's consumed at cluster level needs to be represented in the table associated with the cluster. So the basic idea is that you should be able to figure out the total power consumption of the system by looking at the utilization of each CPU, multiply it by the power consumption for the P state the CPU is in, and the rest of the time it's idle, and then you'll add the idle state transitions. So this is an example of the data we put into the tables for TC2. So at CPU level, because we have on TC2 we have cluster level frequencies, so all the CPUs will share the same frequency in the cluster. But we have per CPU we only have WFI, whereas on cluster level we have cluster shutdown. So for the CPU tables, we would represent all the frequency states, even though they are actually associated with the cluster. We need to know the power consumption for each P state per CPU as well, because we need to know what is the cost of waking up an additional CPU. So if we power up the cluster and just use one CPU and it's running flat out, then we would have the power consumption coming from the P state table from the cluster. That would be the power burned by the cluster, and then we would add 1 times the power consumption of the CPU coming from the P state table associated with the CPU. If we then wake up the other CPU, then we would need to add another CPU contribution. So let's say we were running at the highest P state, 1 CPU. In that case, the cluster would be at the 1024 capacity, and the power would be 4905. So that would be the power consumption of the cluster. The CPU that we woke up, if we only have 1 CPU, then we would have to add 1024 for the CPU as well, so the total power consumption would be 5,929. If we wake up the other CPU, so they're both awake, we would have to add another 1024, and that would give us our total power consumption. So that's basically how it works. The C states, we have associated WFI with the CPU, and we have associated the cluster shutdown state with the cluster group. So the basic algorithm that's in the scheduler to figure out what is the energy consumption. In the scheduler, we don't really care about, or for most decisions, we don't really care about what is the absolute energy consumption. Actually, what we want to know is if we want to move a task from one CPU to another, we just want to know, is this making the situation better or worse? So it's actually just the difference. We want to know, is it positive or negative? So what we do is that we go through the whole schedule domain hierarchy, and based on the scheduler load tracking, we can figure out what is the utilization of all the CPUs. Combining that with the energy model data, we can figure out what is the energy consumption of the CPUs, of the clusters, before and after we move some utilization. And by utilization, that would be a task. If we move a task with a certain amount of utilization from one CPU to another, then we can figure out, does the reduce in energy consumption on one CPU, is that bigger than the additional energy we burn on the other CPU where we move the task? So that's basically how it works. So that's very short how the model is supposed to work. Now, how do you come up with the data you need to put into your tables? So that's the more difficult side of the problem. So for TC2, what we did was that on TC2 we have per cluster energy counters. So we have some registers we can read, and we can figure out how much energy is burned on each cluster. So to come up with all this table data, we wrote various scripts to force the system into specific P states, ran a workload to figure out what is the busy power, and the same benchmark could also measure what is the throughput, or how much computation can we do at each P state. So the P state tables are fairly easy to come up with. The more difficult bit is to characterize the C states, because for the C states, you need to sort of trick your platform into various combination of C states, such that you can actually derive what is the energy consumption of the CPUs and the clusters. So you may want to use CPU idle to disable specific states, and use various workloads to generate wake-ups, such that you can figure out what is the average wake-up cost. We don't have automated tools to help with deriving the C-state information, but I think it should be fairly easy to do if you know your platform well. I saw in the presentation, was it yesterday or Tuesday, from Qualcomm about their CPU idle upstreaming work, where they already have such numbers. So,
in our presentation.
yes.
Can I just?
One of the things that we do get asked about, firstly, like, you already made the point that the model needs to be simple,
yeah.
right? And for all the reasons that, and that's fine. But there is this initial sort of reaction to the energy model story, which is you're asking for a fairly complicated data set to be sort of produced just for this.
Yeah.
It's worth calling out that none of this stuff is not already available for somebody who's writing, somebody who knows this platform and is intending to tune CPU idle or CPU freak for that platform. So it's exactly the sort of information you would already do if you were interested in figuring out what are the latency values and what are the the break-even points in CPU idle, right? So you'll be getting the same information over there.
Yes.
Now, it's interesting to note that we haven't seen a lot of very good tuning being done in the general case, right? So, but if people were doing tuning of their CPU idle and CPU freak subsystems, this data is already available.
Yeah.
It's not like extra stuff.
So, question on the, probably the hardest thing in here to derive presumably is the wake-up energy.
Yeah.
Do we have any analysis that shows how much better decisions you get by adding that extra knob versus just ignoring it?
So to begin with, I didn't have the wake-up energy there. The problem is that if you don't have the wake-up energy, then there is no difference between adding a task to a new cluster. If you don't consider the cost of waking up stuff, then, and you only consider the busy and idle times, then there is no difference in putting a task on a completely idle cluster, because the cost of waking up the cluster is free if you don't take it into account. So you wouldn't bias scheduling in any way to actually try to consolidate tasks within your cluster.
No, but you can associate a steady state power with that cluster being on, right? Without actually worrying about, whether, if you can associate, if it's 50% on and 50% off,
yeah,
you can associate a power with that without caring whether that 50% was wake up and go back to sleep or in and out 1,000 times, right? The wake up energy only allows you to distinguish how many times you went up and went down,
yeah,
right? You can associate a steady state power with the cluster being on that would solve the problem you just raised.
Sorry?
I'm just wondering if it comes, I was going to say something that doesn't make sense. I was wondering whether it would come from the per cluster tables, but it wouldn't, because it's still going to be the same cost on the cluster, whether you want the former than the
Yeah.
right.
I'm pretty sure there are situations where you really want to take it into account the wake ups. Especially the biggest problem is for small tasks that wakes up all the time, because what we found was that for those tasks, the main energy consumption actually comes from the transitions of coming in and out of idle. It's actually not the task running. So for those tasks, you want to know if you put it on a CPU. If you put it on a CPU which could be in a deeper idle state, then you would burn more power, because it will be transitioning in and out of a deeper idle state. I mean, if you have a CPU which is already running something, so it's kept in WFI when it's idle, or you have another one which can go into per core, power down, whatever you have, then if you don't have the transition energy in there, then it wouldn't make any difference which one of them you put them on, because you don't have the extra cost of waking up from per core power down versus WFI. And it's a lot cheaper putting that task on a CPU which is in a more shallow idle state, because the transitions are cheaper.
Yeah, so that makes sense. And now, to solve that simple example, you could just have 1, 2, 3 right? And you prefer waking the shallower core, but if you create a more complicated example, maybe. But that also assumes now that as part of your workload tracking, you know the wake rate.
Yes.
Right, so that's there already, or that's something that has to be added?
We have added that, but it's quite easy to track. I use the existing code for the geometric series and all that, and I basically just add one every time the task wakes up, and that number decays over time. So I use that to try to figure out what's the wake-up calls when we have to place a task on a specific CPU. So I think it's fairly low overhead to actually track that.
Yeah, I was just going to ask, so in our solution, we're not doing the wake-up rate thing. We're just sort of on every wake-up, we're preferring CPUs that are in shallower C states, trying to avoid the problem you mentioned. So what sort of difference would you expect between those two approaches?
That's a good question. I haven't tested the other approach, but I think we should try to do it. I mean, if we can avoid tracking the wake-ups in any way and get similar results, I think then I'm happy to drop that. To me, it just seemed necessary. But if we can get to the same results, then I'm happy to just consider the actual C state of wake-ups.
Yeah, I haven't wrapped my head around, I guess, what the behavior difference there would be, but it does seem functionally simpler. But yeah, I guess just have to be tested. So.
Yeah.
It would be interesting to see if you just take your model and rather than plugging in a real wake-up energy, you just put 2 for power collapse and 1 for WFI.
Yeah.
How that actually affects the behavior, right?
Yes.
But this means that the energy and the transition is the same on big and little CPUs, for instance. If you have a value in your table, then you can actually tweak it and customize it to the actual CPU. If this is necessary, but I don't know.
Yeah, I mean, having a number there definitely adds more information, so we should be able to make better decisions, but whether it makes a difference in reality, that's to be seen.
Trading off the complexity against the benefit.
Yeah, but if we can get rid of it, then sure we should do it, because it simplifies the model, and it's already expensive. Well, it looks very simple, but we need to use it.
Not just that. The difficulty with a lot of this is we're asking a vendor to provide quite a lot of data.
Yes.
So there's a lot that you could get wrong.
Yes.
Yeah, I mean, there's obviously other, the transition energy is going to vary based on what P state you're going in and coming out from. So
yeah,
it's still, even with this, it's not perfect, right? No. So it's unclear where the right point to draw the line is. Right?
Yeah. I just found that completely ignoring wake-ups, that's not good enough. We need to have something there, but how much? I agree, that's not really clear yet.
Yeah. No, I mean, if you get the full solution, then I guess you can experiment with various levels of back off and see how it behaves, right? So it's good.
Sure.
What we need is platforms that have really rich power states. Yeah, what we need is platforms that have really rich power states. I don't know if you know any company that might have some,
So I gather the important thing about the wake-up thing isn't so much, or maybe not so much, that whether that you take into account somehow, if you have estimates that, because you can't directly measure it, you say, well, this chip is like this other one on the market that has this value, then I'm going to use similar value type of thing. Would you still be able to get most of the benefit, or not, if you just could do that much? So you understood my question.
Yeah. Well, the more accurate the numbers, the more right the decisions will probably.
No, I know, but I mean, is there any value at all in making a hopefully reasonable estimate, if that's all that you can do, or does it make the model not useful all of a sudden?
I mean, the numbers we put in there, some of them are really estimates, because measuring the energy of transitioning in and out of very shallow idle states is almost nothing. I mean, it was really, really hard just measuring the transition of bringing up and down the cluster. And actually, the numbers we have in the table are, actually multiplied by, what is it, do we shift it by 3 or 6? It's already tiny numbers for the wake up, so it's only a tiny bias. So if you get it slightly wrong, I don't think it makes a bit difference.
And also, are the values you're going to get consistent from part to part, or are they going to vary a lot?
That's another question. I don't know what the variation is.
I mean, for instance, coming from Qualcomm, although we don't generally ship the original old versions of a new chip that's coming out, we often go through several iterations, or we have some special iteration that goes into like a higher performance, higher, cost version of the same thing and call it such and such pro or that type of thing. And you'd have to go in through for every single one of these and A, know which one you're really running, and B, get the correct values for those so that you're actually using the information for the part you have rather than the one that maybe you thought you had.
Yeah.
That's a good point.
So I'm just saying there's a lot of work, and there's more work here than meets the eye, I guess is maybe what I'm worrying about. And then the other question I had, which is totally unrelated to this thing, but I saw it, you have this big loop about, for every, it looks like for every CPU, the big loop there that calculates whether you're benefiting from going from one, I assume that's, benefiting from going from one core to another core. Suppose you have a server-like system that has lots of processes and lots of cores, wouldn't that tend to get real expensive?
It does get really expensive, and that's one of the fundamental problems that we'll have in this whole EAS approach, is that to figure out the difference in energy or the power budget, you basically need to go all the way to the top to figure out what implications a change would have.
Right. So you're doing this effectively for every process, for every core, or isn't that?
So we don't do it for every CPU. It's sort of a tree like the diskette domain hierarchy I showed you before. So we start at the bottom at the CPU, and then we go up to the cluster level and see what impact we have at this level. And then we continue up the hierarchy, but we don't do computation for. We don't necessarily have to do computation for all CPUs in the system. We can actually back off if we can see. For example, if the cluster has a CPU which is already 100% loaded, then adding another CPU to that cluster won't affect the energy consumption at the cluster level. It will only add the extra energy of an extra CPU.
So in some cases you can say, we don't care about the result of this part of the computation and just keep going.
Yeah, so sometimes you don't have to go up to the highest level.
All right, that's good, because I'm worried that that's not what you have there.
Yeah.
Scale well.
Thanks. I just wanted to add that those for each CPU things you saw here, they are already heavily used in the scheduler code. So if you want to do in task wake up, for instance, to find the right CPU or do the right thing in the load balance path, those loops are already there. So we just have to hook in with the energy aware stuff intelligently, so we don't add extra code necessarily. If you have like a system with a lot of CPUs and you have a lot of hierarchies, you already have to go through this code a couple of times.
Well, you won't increase the number of loops, but you'll increase the work during the loop.
Yeah, that's true.
I think there's a question back here.
Do you consider frequency even in your idle and P states, C states and P states? Because at different frequencies, the overhead could be different. The overhead and the idle state.
In the idle states, no, I don't do that right now. I don't know how much difference it makes. I mean, TC2 is a quite restricted platform. That's what I've been using so far. So.
Okay. Actually, we have that data.
Sorry?
I think give you that data for TC2.
Okay.
But I think that's a question of whether you want that though, because for every possible set of all the combinations of any state, you have to transition from there to there, and so you exponentially increase the state machine, right?
Plus, you might have some platforms that auto go to put down the entry.
Yes.
So, and plus like the discussion.
So it kind of gets back to that, even the wake up, cost thing, which is that where do you draw the line on what's genuinely worth modeling and what's not, and there's no easy answer.
There's a question of useful accuracy.
Yeah.
You need to be accurate enough just to influence the behavior.
But actually adding to maybe
If the more accurate, more often you influence it correctly, the less often you influence it.
But the question is whether you...
No, I understand it's a trade-off, but I fear the trade-off may be different depending on, how important it is to get the scheduling part right versus, just the performance in the system. We usually running cycle, just calculating all this stuff and deciding the trade-off.
Yeah. I guess the reason I say that as well is because we speak to a lot of, you present this to a CPU designer and he'll just go, but this is nonsense because, it actually depends on the loading per thread, for example, is going to be, the costs are going to be completely different whether I'm doing float, whether I'm doing integer, right? Or the other one will be, it also completely different depending on how memory bound I am, So the kind of level of detail that you can put into this is just like endless.
But what if this guy gives you a whole lot of neon instructions?
Right. Well, we know those numbers. We know that's significant, and what we would like to do better at is articulating that with tangible workloads, controllable workloads.
So about the complexity, it's worth calling out that yes, there are, depending upon the hierarchies you have in your design in terms of, SMT, SMP, beyond, multi-cluster, and so on and so forth, you probably have to invest more time in hot paths, decide your energy diff function perhaps needs to do more work. But remember that we're currently focusing on a class of machines over here where you truly do not have very complicated hierarchies anyways, right? That's one thing. Second thing is that we know for a fact that the energy path, the scheduler pathways are pretty darn complex already, right? So this is not adding a significant delta to those pathways, right? There's a lot of work that happens over there. That was this bit. Secondly, we know we want a simple model in to get the machine moving. That does not preclude partners from considering adding other dimensions to the energy model that considers different instruction mixes. We're focusing purely on integer-heavy stuff over here. But that's improving the status quo already from our viewpoint, right? So if partners wished, they can embellish that further and say, all right, so we want to add another access to that, which is neon heavy, or floating point heavy, etc. We just don't have the luxury of doing that because we need to keep it simple. And, well, we do think about that, of course.
And I think maybe a recurring theme is that there will be some need to change the table at runtime. There's like the initialization time stuff, which Larry was kind of, I guess you were more or less bringing up binning earlier, right? Yeah. And so if you have adaptive voltage scaling or something, and that may be a one-time table change at init, where it's like, oh, on this, it's a cold chip, so we can change the power numbers a little bit. And then Steve was talking about the thermal stuff, which will be like dynamic, changing of values. But it seems to me that that's something that will definitely be recurring.
So regarding the criterions used for this optimization, so the algorithm gives a number, and obviously a bigger number saving is better.
Yes.
What are the constraints the optimization algorithm tries to do the best under? And concerning the previous claim about the dynamic changes, the thresholds might be changing. Maybe the tables should stay static, but sometimes you cannot pay more than some amount of energy, for example, because you're thermally marginal.
Yes.
And this should affect the way the algorithm takes the final decision.
Yes. So I guess your first question is what is the power performance trade-off? So the current algorithm will try to save as much energy as possible without overloading any or starving any task. So the assumption is if we move a task to a CPU, it will only do that. It will simply back off if there is not enough spare capacity on the CPU to take the task that we're trying to move. So we try to avoid hurting performance as much as we can while picking the cheapest CPU to put the task on. And I think that works fairly well, but yeah, we need to do more testing on that. And regards to the thermal aspects, they will have to come in to this at a later point. But right now, we have different people working on trying to solve the thermal issues. And at one point, we will have to coordinate our work with what they're doing. So right now, the only thing we can probably deal with is if you cap P states, for example. You could do that, and this would still work, I think. But we need more coordination at one point. But right now, we don't consider the thermal issues here. Do you want to say anything about that? Thermal constraints.
The convergence.
So ultimately, the question is, if there is a way to block certain level of penalty, not by means of plug and plug, by means of something organized and fast.
So, just give me a standard spiel of integrating IPA in there.
Yeah.
Right. So, I don't know if you looked at the stuff that we've done with the thermal management, but we have this notion of actors, of which CPU is one of them. And the idea is that you'd give, so you basically, the idea is that would give the energy-aware scheduler a power budget, and it would have to schedule within that power budget. So, to do that, it can do two things. One is it can choose lower OPPs, and the other one is that it can shy workload away from cores to achieve that power budget. So it's exactly what you're saying. It would be, it wouldn't be as heavy as a hot plug semantic. It would be more a way of influencing the scheduler to effectively inject idle states. And we haven't done any of that yet, but it's what we're thinking about.
But we see our friends at Qualcomm have already done similar things on capping
Biasing tasks, right? So the methodology is proven.
Okay, I think we're out of time, so thank you very much.
Can you share the slides?
They'll all be on the Linaro website. Okay,
it's not there now.
Sorry?
It's not there now.
Yeah.
Okay, put it up there.
Then you just sent it to me, so it'll be there.